start with the pole placement by state feedback part 3. In this we will study design of state feedback controller using pole placement approach, that is Ackermann's formula, and whatever technique we will study that is based on Ackermann formula, that means we will solve a numerical example based on this Ackermann's formula. Now, design of state feedback controller using pole placement approach, that is Ackermann's formula. As our system is a state space system, so that state space system is x dot equal to Ax plus Bu, and here output is y equal to Cx plus d, Cx plus d. This is your plant, and for this plant we have to design a controller, that is we are designing a controller that is Kc, and previously we have seen that your control law u equal to minus Kcx plus r, this is our control law. And here all this methodology designing of the controller is basically concerned with this equation only, x dot equals to Ax plus Bu only, and law is concerned with this same u equal to minus Kx plus Kcx plus r, this is your control law. So, these are relationship between this and this, and in that there is a one part coming a controllability issues QC, controllability B a b a raised to n minus 1 b, and one important thing which will come, that is the desired pole. In this will come a desired pole, that is say Qd, which is the desired poles. That means the designing of controller in a state space, it depends upon a state space model x dot equals to Ax plus Bu. Second, it depends upon the control law, that is u equals to minus Kcx, this is case, that is control law is u equal to minus Kcx plus r, this is the control law. Then it depends upon the controllability matrix Bab a raised to n minus 1 b, and Qd is the desired poles. That means now whatever the formula which will get, it depends on these 4 conditions 1, 2, 3 and 4. So, we will find that based on these conditions, the Ackermann has proposed a formula for the designing of the controller. So, controller design using the Ackermann formula, it gives as 0, 0, 1. Now, here this is QC, which is controllability matrix inverse, into phi of A, this Q of C is nothing but B a b a raised to n minus 1 b. So, controllability inverse into phi of A. So, that is very important formula, we can directly get the controller, there is no need for any iterative approach. But now how to get this particular formula, that is particular this formula, how to get this formula? Now, we start deriving the Ackermann formula, and the technique which we use here to get this is a Cayley-Hamilton theorem, as we have seen that earlier in getting the state transition matrix, that is Cayley-Hamilton theorem says that every square matrix is satisfied own characteristic equation. So, this phi of A is nothing but the original characteristic equation, which is in terms of eigenvalues or in terms of lambda, in terms of characteristic coefficient, that has been represented by phi of A. So, that is basically a Cayley-Hamilton theorem, that is Ackermann formula is nothing but the use of or basic of this is Cayley-Hamilton theorem. Now, we start deriving the result. So, again we start writing down original plant x dot equal to Ax plus Bu, u equal to minus Kcx plus r, and here your x dot A minus B Kc into x plus B into r. Now, the characteristic equation in terms of lambda, lambda I minus A minus B into Kc, and now here this lambda I, this A minus B Kc we can write down as A bar. Now we have desired eigenvalues or the poles which has to be placed. So that desired eigenvalues or poles we can write down as desired eigenvalues at lambda 1, lambda 2 to say lambda n. So here this part which we have got based on the control law. So this control law is working like this, and we have desired poles. So desired poles are lambda 1, lambda 2, lambda n. So based on the desired poles we can also write down the characteristic equations. So based on the desired eigenvalues, the characteristic equation we can write down as lambda raised to n alpha 1 lambda raised to n minus 1 alpha 2 lambda raised to n minus 2 plus alpha n equal to 0. This we have got. Now we have to develop a formula, but when we go for nth order you will find that to determine the inverse and determine the characteristic equations it may be difficult, particularly from a derivation point of view. So normally when we do the derivations or to get a generalized results, for sometimes what we are doing, we are going for some lower order. Once we get a result for lower order, then we can prove that the similar result we can obtain for the nth order system. So here for simplicity what we are doing, we will design the controller for n equals to 2 only. That is the controller Kc which we should get 0 1 BAB into phi of A. This is to be determined. Now according to Cayley-Hamilton theorem, what we can write down, this phi of A equal to A bar square plus alpha 1 into A bar plus alpha 2 into I. Here you will find that this is your the characteristic equations lambda, lambda n, and now here our original plant is A, but because of the control law this A has been changed to A bar. So A bar plays an important role, and therefore based on the desired eigenvalues we can write down as phi of A bar square plus alpha 1 A bar plus alpha 2 into I. This is basically for when n equals to 2. Now we will find that this A bar equal to A minus B into Kc. Now this A bar, you see here this A bar is nothing but A minus B into Kc, but in the equation we require A bar square. So what we can write down, this A bar square equal to A minus B into Kc whole square. So now there is need to solve these equations. So here we can write down this as A minus B into Kc multiplied by A minus B into Kc. Now if you multiply A with respect to A B Kc, so you will get A square minus AB into Kc minus B Kc into A plus B square into Kc square. Now here after solving this we will get A square minus AB into Kc minus here BKC is common, so we can write down as B into Kc, get A minus B into Kc, and we know that is A minus B Kc is equivalent to A bar. So we can write down this equation as a square minus ab into kc minus b into kc into a bar. So, we have got a bar square. Now, here this phi of a actually basically is phi a bar. Now, we have got these equations. Now, what we will do? We replace this value and see what type of results we can achieve. So, here phi a bar, that is equal to alpha 2 into I plus alpha 1 into a bar plus a bar square. So, a bar we know a minus b k c, that is our now the desired means that we are getting after the controller is come into existence. So, now this is the equations we are written according to the Cayley-Hamilton theorem. So, alpha 1 I, alpha 1 a bar square. Now, we replace the values of a bar and a bar square in these equations. So, we can write down this as alpha 2 into I plus alpha 1, what is a bar? A bar is a minus b k c, b k c, k c is a controller, plus a minus b k c whole square. Now, we solve these equations, we will get alpha 2 into I plus alpha 1 into a minus alpha 1 b into k c plus, now this is a minus b k c square. So, we can write down as a square minus this is a bar, a minus b k square, that is a bar a b into k c minus b into k c into a bar. Here a minus b k c square, that is nothing but a bar square. So, a bar square we have already determined. So, simply without solving here we have replaced the value of a bar square as a square a b into k c minus b k c into a bar. Just see here this part is nothing but this one, and this portion is nothing but this one. Now, again we simplify these equations. So, we will get alpha 2 into I plus alpha 1 into a. Now, what we are doing, the terms concerned with the a we have taken on one side, particularly we have taken alpha 2 I, alpha 1 a plus a square. Now, here alpha 1 b into k c minus a b into k c minus b k c into a bar. As we have got phi a bar as a square plus alpha 1 a plus alpha 2 a, but if you write the equation as phi of a is nothing but a square plus alpha 1 a plus a square. So, this phi of a, this particular equation, it is of the original system A, because original system also satisfies the Cayley-Hamilton theorem, because here we have seen that Cayley-Hamilton theorem condition we have determined point a bar. So, a bar means we have got this portion, and when we talking about a is the original system, the Cayley-Hamilton means theorem says phi of a equal to a square plus alpha 1 a plus a square. So, we will find that this particular equation we write down as phi of a minus alpha 1 b into k c minus a b into k c minus b k c a bar, and this is 0. Now, we will see phi of a, that is equal to alpha 1 b into k c plus a b into k c plus b into k c into a bar. So, what actually we have done, this phi of a bar that equal to 0. So, we can write down this equation as phi a minus this equal to 0. So, finally we have written the condition in terms of phi of a equal to alpha 1 b into k c plus a b into k c plus b k c into a bar. Now, here what we can do, we can take out this b common here from this part, this and this we can take b common. So, we will get alpha 1 into k c plus k c into a bar plus a b into k c, and therefore, this phi of a we can write on a b a b as alpha 1 into k c plus k c a bar, and here as k c. So, we written equation in terms of a phi of a equal to b a b alpha 1 k c a bar into k c. Now, what we will do, we pre multiply both these equations by 0 1, and prior to this one we will write the equation as b a b inverse phi of a equal to alpha 1 k c plus k c a bar into k c. Now, here we pre multiply the both side by say 0 1 matrix. So, we can write down as say 0 1 b a b inverse say phi of a to say 0 1, and here we will get, we can write down as alpha 1 this k c plus k c into a bar, that is equal to k c. Now, after solving it, so what we will get, this k c equal to 0 1 b a b inverse into phi of a. So, this is the controller which is determined, and particularly the phi of a here we have considered as the desired cast equation. So, whatever the desired cast equation is there, we write in terms of lambda and replace that lambda by a. So, this equation we have determined for when n equals to 2. Now, how will you how will you write the controller design equation when for any values of n? So, for any arbitrary positive integer n, we can write down as this k c is controller as 0 0 0 1 b a b a raised to n minus 1 b inverse into phi of a. This is the controller design. So, you will find that here k c equals to 0 1 b a b inverse phi of a, that means same thing here 0 1, this is q c inverse into phi of a. Now, just see it again. So, we have a state space model x dot equals to a x plus b u, we have control law. Now, here the controllability matrix. So, here what we are done here, this a minus b k c we can write down in terms of a bar. So, desired eigenvalues, that is lambda 1, lambda 2, lambda 1, that can be written in terms of this one, and this phi of a bar we are written in terms of a bar square alpha 1 a bar alpha 2 I, that is for n equals to 2, and now here we are simplified, and here this alpha 2 I alpha 1 a plus a square we are written in terms of phi of a, and finally these equations we are written, and we come across the finally all doing all the steps, the controller k c equals to 0 0 1 q c inverse into phi of a, and this is the final controller for the nth order system. Now this controller is designed, and this basically called Ackermann formula. This controller which we defined Ackermann formula, and this depends upon the Cayley-Hamilton theorem. Now we start solving one example. So we will take the same example which we have taken earlier, that is we have solved earlier example which is based on state transformation. So same example we will try by means of Cayley-Hamilton theorem, or that means we will solve by Ackermann's formula. So here original system as x1 dot, x2 dot, x3 dot 0 1 0, 0 1 1, 0 minus 1 minus 2, here x1, x2, x3, 0 0 1. So this is the same plant. Here there is no need for any output equations. Now the desired poles, the desired port which we have considered earlier, lambda 1 2 as minus 1 plus minus j root 3, and here lambda 3 equals to minus 10, and based on this we can get the equation as lambda plus 1 plus j root 3, lambda plus 1 minus j root 3 plus lambda plus 10. So if you solve these equations, you will get lambda cube plus 12 lambda square plus 24 lambda plus 40. So now this is the desired characteristic equation, and now here according to Cayley-Hamilton theorem we take phi of A as A cube plus 12A square plus 24A plus 40 into I. This is phi of A. As the controller K involved 0 0 1, controllability inverse QC inverse into phi of A. So phi of A already we can determine, means phi of A formula is given. So replacing the values of A in this equation we get phi of A. Now there is need to determine the controllability inverse, and 0 0 is one it exists, and after multiplication we can get the controller Kc. So now first of all we determine the controllability matrix QC as B AB A square B. So the values of B here 0 0 1, AB as 0 1 minus 2, 1 minus 1 3, this is QC. Now this QC is there, but in actual formula we required QC inverse. So the inverse of this we will get QC inverse as minus 1 2 1 1 1 0 1 0 0. Now QC inverse we have got. Now we require the phi of A. This phi of A equal to A cube plus 12A square plus 24A plus 40. So what we have done here? We will find that here we have got the equations, that is the desired equation as lambda cube plus 2 lambda square 24 lambda plus 40, that is by desired. And now what is say that the Cayley-Hamilton that this equation has to satisfy the own characteristic equation. So characteristic equation means we are trying with the A matrix. So A square A and this one. So here we will find that this A cube plus 12A square plus 24A plus 40. So here if you solve it or replacing the values of A in this equation, and after solving we come across the result as 40 36 11 0 65 plus 14 0 minus 14 plus 23. So this phi of A we determined, QC inverse we determined, and now we can write down the formula as Kc equal to 0 0 1, here we get minus 1 2 1 1 1 0 1 0 0. This is basically your QC inverse, and this phi of A we can write down as 40 36 11 0 14, then 0 minus 14 is 23. Now, after solving these equations, particularly we solve this with this, so we will get 1 0 0, and here this will remain as it is 40 36 11 0 14, and here 0 minus 14 23, and again cross multiplying we get 40 36 and 11. So, now this is the controller KC. So, we will find that by means of Ackermann formula we have a design a controller. So, this controller will stabilize our system, and whatever the performance we have specified, that can be achieved by the Ackermann formula. So, based on Ackermann formula we have got the controller design, and if you have seen the various steps here. So, what we have done here? Here we have taken the plant as A plant, then we have taken a controller u equals to minus Kcx plus R, and then this is the characteristic equations, then lambda I minus A bar. Now, where we have a desired eigenvalues in terms of lambda 1, lambda 2, lambda n. So, these are the equations. Then as our the system has changed to A minus Bk Kc into A bar. So, we have written equation in terms of A bar, but as for simplicity purpose we have taken n equals to 2, and then we have solved this equation, and somewhere we have got lambda alpha 2i alpha 1a plus a square. Then this has been written in terms of phi of A. So, alpha 1 Bkc A Bkc Bkc A bar, and again after simplifying everything we have got this particular equation 0 1 QC inverse into phi of A, and similarly we have written for the nth order plant, that is here 0 0 0 1, this is QC inverse into phi of A, and based on this one example we have solved. First, for in this example what we have done, we have decided the desired poles. So, the desired poles we have written, then we have determined the characteristic equations, and then once these characteristic equations we have determined, that has been converted in terms of A matrix, that is according to Cayley-Hamilton theorem. Then controller Kc equal to 0 0 1 Qc inverse into phi of A, and then we have used the different steps, and finally we got controller Kc as 40 36 and 11. So, here we have seen the two methods for the controller design. But here there is an one important issue which you might have identified. Here all the controller has been designed based on Ax plus Bu. There is no role of y equal to Cx we have observed. State has been controlled by means of state equations, but the y equals to Cx, so that part cannot taken into existence. So, by doing all these things, can we have, did we got means have we achieved a completely desired performance? Definitely there is something problem is involved. It is because if you write any transfer function Gs in terms of numerator and denominator. So, if you write down this as let us say s plus 1 s square plus 2s plus 3, and if you convert this in terms of AB matrix, so A is 0 1 minus 3 minus 2, and B matrix as 0 1 and C matrix as 1 1. So, the system of like this, and we are mainly concentrated on s square plus 2s plus 3, and we have designed a controller, but this s plus 1. So, s plus 1 is called the zeros of the system. So, when the zeros are not placed, are not have not been utilized in a controller design. So, definitely when we determine the actual performance, this may create some problem to our system performance. Therefore, there is need to tackle these issues. So, in the next part we will see how to handle the effect of zeros, or in other words how to handle the effect of C matrix in a controller design. Now, these are some references: Kushkishore Ogata, then D. Roy Chaudhary's, then Nagaraj Gopal and Dorf. So, you can use these references for more detailed study. Try to solve as many examples as possible. Thank you.